paper, paints, detergents, fabrics. The development and application of fluorescers embraces some of the most significant scientific discoveries of this age. What is the nature of fluorescent light? And how does the organic chemist control it? When a molecule absorbs energy, it is lifted to a higher energy level, or excited state. Then, releasing surplus energy as radiation, it drops back to its stable or ground state. Fluorescence occurs when energy is absorbed from one part of the spectrum and given out in another. The explanation is to be found in the relationship between energy and matter. Molecular systems absorb or emit energy in quanta. Quanta are discrete amounts of energy which can be relatively large or small. They are related to wavelength. The bigger the quantum, the shorter the wavelength. The smaller the quantum, the longer the wavelength. So there is a specific relationship between quantum size and the electromagnetic spectrum. Above the visible range is ultraviolet, and below it is infrared. If a fraction of a quantum is lost, the remaining or emitted quantum is smaller. Take a beaker of water and add a fluorescent agent. Expose it to ultraviolet radiation. Ultraviolet is absorbed. Some of this energy is dissipated, and the remainder is emitted as visible light. This could be green, red, or blue, according to the amount of energy lost. When the ultraviolet light is switched off, fluorescence stops. So a fluorescent agent absorbs energy at one level and emits it at another. The most useful are carbon compounds, and the explanation of their behavior is found in the double bond of organic chemistry. Take 2 atoms of carbon and 4 atoms of hydrogen. The hydrogens are bonded to the carbon atoms, and the nuclei of the carbon atoms are also bonded to each other. These bonds are all strongly held electron clouds called sigma bonds. But there are spare electrons on the carbon nuclei. They're attracted to the opposite nuclei and pair off to form a second bond, a pi bond. This second bond, unlike the sigma bond, is external to the carbon nuclei. It is a less stable part of the molecule and is known as a delocalized area. These pi bonds are the key to the phenomenon of fluorescence. Indeed, the practical application of fluorescers depends largely on the controlled extension of the pi bond system. The ethylene molecule helps to explain this. In its normal or ground state, a molecule is stable. When it absorbs large quanta of ultraviolet energy, the pi bonds, the external bonds, are broken, and antibonds form in their place. The molecule has been lifted to a higher energy level. This extra energy is held temporarily, but the antibonds are unstable and will return eventually to their original form. But in the process, small infrared quanta are lost as heat. Fluorescent light is emitted when the molecule loses its remaining surplus energy in returning to its stable state. The simple illustration of a molecule in the ground state shows what happens. The molecule can absorb 1 or 2 or more quanta of infrared and as easily lose them. When the molecule absorbs a large quantum of ultraviolet energy, it is lifted right out of the ground state to an excited state and temporarily occupies one of its higher heat energy levels. Some infrared energy is first lost. Then the molecule, because of its continuing instability, falls to the ground state, emitting its surplus energy as a quantum of light. This is because the absorbed energy has already been lost as infrared, so the emitted quantum is smaller than the ultraviolet quantum. If the right quantity of infrared energy has been lost, the emitted radiation will be visible light. To build molecules which absorb energy quanta from just beyond the region of visible light, and after the loss of infrared energy, emitted in the visible part of the spectrum, is the task of the organic chemist. Ethylene illustrates the principles of fluorescence, but it cannot be used in practice. The area of delocalization formed by the pi bonds is far too small and cannot be easily disturbed. We can extend the area by joining ethylene molecules together. This, in theory, would create a molecule that would fluoresce visibly. However, it would be neither efficient nor chemically stable. The necessary stability can be found in benzene. Benzene can be considered as 3 ethylene groups. Joined together with the loss of 6 atoms of hydrogen, sigma bonds form. Above and below, pi bonding extends to form continuous rings. Although the resulting molecule is chemically stable, it is still not a practical fluorescer. But take a central ethylene group with its relatively small area of pi bonding, flank it on each side with a benzene ring, the area of pi bonding is greatly increased, and you have made stilbene. Add other groups, for example those containing nitrogen, which help to increase the delocalized area further, and you have made a good fluorescer. It emits light strongly in the blue-violet region of the spectrum. But at the stage of practical application, problems arise. The fluorescer will adhere to cotton, but it still has to be made soluble in water. So hydrophilic sulfonate groups are added. It can now be used as a fluorescer for cotton. But this fluorescer does not adhere so well to nylon, so the chemist must synthesize other molecules. For example, in place of the ethylene bond, a nitrogen-carbon double-bonded group is introduced. The benzene rings remain. But the fluorescence is too green. Other groups must be added to move the fluorescence into the blue region of the spectrum. Now the molecule is suitable for brightening nylon. 2 of many problems associated with providing fluorescers for use in domestic detergent solutions. A molecule must not only be stable, it must adhere, and adherence requires different properties for different fibers. The conditions in which fiber and fluorescer come together may be vital. The detergent solution itself may affect the behavior of the fluorescer. No piece of engineering is more specific than a fluorescent molecule. There are many variants of all these molecules, and with the new man-made fibers of tomorrow, there must be even more. Fluorescent molecules must have the ability to absorb, dissipate, and emit radiant energy, the basis of fluorescence. Fluorescent molecules are lifted to an unstable level by the absorption of ultraviolet energy. Infrared energy is lost, and fluorescence occurs as the remaining energy is emitted in the visible part of the spectrum. The association of the organic chemist with the practical application of his work, the constructive marriage of research and commercial objectives, has made the world a more colourful place, to be seen from now on in a different light.